So section 10.3 is going to go over some more stuff on radical expressions and specifically simplifying them. So we've already seen how to simplify them a little bit using some rational exponents. Now we're going to get into how to simplify radical expressions that are not perfect squares. We're also going to go over the product rule and quotient rule, which quotient rule we've actually already seen a little bit, but we didn't put a name to it. So we'll see that after we talk about the product rule. So the product rule, and this is a really important concept or formula to kind of get down, is if we have the nth root of A times the nth root of B, and so notice how they are both the nth root, then we can go ahead and multiply the stuff on the inside, so we get the nth root of A times B. And so one thing to note here is that the index must be the same. So if you're multiplying a square root by another square root, you get a square root. If you're multiplying a square root by a cube root, we can't combine those because they wouldn't have the same root. So let's go ahead and look at some examples. So we're told to multiply. You could also just be told to simplify. That would also mean go ahead and multiply them together. So this first one here, we're given the square root of 5 times the square root of 13. And so first thing you want to look for is, are these both the same root? Do they have the same index? Well, they do because they're both square roots. So then we're going to go ahead and multiply 5 times 13. So 5 times 10 is 50. 5 times 3 is 15. 50 plus 15 is 65. And we're going to keep that square root. And that is all we're doing for right now. So we're just multiplying them together. And in these ones, we're actually, most of the time with these, you won't be able to simplify because you're going to get numbers like this that you can't really break down. We will see one way you can simplify it, but let's go ahead and try a couple more of these. The square root of 10y times the square root of 3k. Now notice for this one, we have, they're both square roots again, so we can multiply them. Now, if we're doing 10y times 3k, if we were adding, we wouldn't be able to combine these because those aren't like terms. But when we're multiplying, remember, we don't need like terms. So we're going to multiply the coefficients. So 10 times 3 is 30. And then we have a y times k. So you're just going to put y k or ky. It doesn't matter which order you put those in. Typically, they'll be in alphabetical order, but it's right either way. All right, number 3. We're given the cube root of 2 times the cube root of 7. So again, let's make sure that we can actually multiply these. They are both cube roots, so that's good. Now let's go ahead and multiply what's on the inside. 2 times 7 is 14. So we get the cube root of 14. Notice how the index is never changing. We don't do anything with these 3's. You don't add them, multiply them. You just carry it on over to your answer. All right, let's try another one here. Let's do the 6th root of 8r squared times the 6th root of 2r cubed. Now with this one, again, we have the 6th root for both of them, so we can multiply. 8 times 2 is 16. R squared times r cubed. Now remember, when you have two things that you're multiplying, you want to add the exponents. So we get r to the 5th, and then bring over the 6th root. Okay, and then a couple more here. Number 5, the square root of 10 times the square root of 10. Now, these are both square roots, so we can multiply them. And when we multiply these, we have 10 times 10, which is 100. And for this one, you can actually go ahead and simplify it down. So the square root of 100 is 10. Make sure when you can simplify, you do simplify. One other trick, something that you should notice here is that we had 2 square root of 10s and we ended up with just a 10. The reason why that happened is if you multiply something by itself, this is the same thing as the square root of 10 squared. And if you remember, if you have a square and a square root, those are inverse operations, they cancel out, kind of like addition and subtraction, and multiplication and division. So those cancel and we just get 10, which is what we had over there. So that's why that happens. One last one, just so you can see when we can't do this. Let's say we had the square root of 7 times the cube root of 5. Always make sure you double check to see if the indices are the same. So because they have different indices, this means that we cannot simplify it. So this is as simplified as it gets. All right, now let's take a look at the quotient rule. And this is one of those rules that we saw briefly before. Kind of mentioned it in passing, but we haven't actually defined it yet. So for the quotient rule, let's write out the quotient rule first and we'll do some examples. If we have the nth root of a fraction, so a over b, then we can split this up. We have the nth root of a over the nth root of b. Couple things to note here is that it works in both directions. And there will be some times when most of the time we'll be going from the root of a fraction to them being split up. That's because we don't like fractions inside radicals. You can also go the other direction though. So that'll be more helpful for a couple things that we'll see. So kind of point that out. One other thing is that if you are going backwards, just like with multiplication, the index must be the same again. All right, so let's go ahead and look at some examples. So here we're told to simplify. They might also just say divide. Either way, we're simplifying. First one we're given is the square root of 100 over 81. Now, this is just like one we've seen before. So what we're going to do is we're going to split this up. So we have a square root of 100 over the square root of 81. Just put the square root on the top and the bottom. And then on the top, square root of 100 is 10, and the square root of 81 is 9. So these ones they work really nicely. It's just a matter of splitting it up and then taking the root. So let's go ahead and try another one. Square root of 11 over 25. So one thing you might notice here is that the 11 on top is not a perfect square, but we can still go ahead and split this up. We'll have the square root of 11 over the square root of 25. And at this point, you just want to simplify whatever you can. So we can't take the square root of 11, so I'm going to leave that on top. But the square root of 25 is 5. So we can simplify part of that, just not the whole thing. All right, number 3, they're going to start to get a little bit more complicated. We have the cube root of negative 125 over 216. Now, what I intentionally did on this one, just so we can see this kind of first step, this negative out in front, couple things you could do. Since we know the cube root of a negative is going to be a negative number, we can take out the negative out in front and then just leave it like 125 over 216. Do it that way. Or you can do what I'm about to do and put the negative on the top or on the bottom, but not on both parts of that fraction. That way, when we split it up, if it were on both, a negative over a negative is a positive, which isn't what we want. So you can do this or do it this way. So I'm going to leave the negative on the top. So we're going to have the cube root of negative 125 over the cube root of 216. That way, negative over a positive is still a negative, which is what we started with. And now the cube root of negative 125 is going to be negative. And what number times itself 3 times gives you 125? That'll be 5. And what number times itself 3 times gives you 216? That one is 6. So negative 5 over 6. You would get the same answer doing it this way. You'd leave that negative out in front, do the cube root of 125 over the cube root of 216. And so you'd still get a negative 5 over 6. That negative is just kind of more out in front doing it this way. So it's up to you guys, whichever one you prefer. All right, number 4, we're given the square root of y to the 8th over 16. So again, first thing we want to do is split it up. So we have the square root of y to the 8th over the square root of 16. And now, if we look at the square root of y to the 8th, we haven't seen these. This was back in section 10.1, I think. We saw these briefly. There was a shortcut, but what we're looking for here is 2 terms that when we multiply them together, we get y to the 8th. And remember, we need to have the same number in each of these boxes here. And so we're going to have y to the 4th times y to the 4th. Sorry, no, yeah, because it's y to the 8th. I was looking at the 16 for a second. Because then when we add our exponents, 4 plus 4 is 8. So this one is going to be y to the 4th on top. If you remember the shortcut here, you're going to take your exponent, so the 8, and divide it by the index, which in this case is 2. 8 over 2 is 4. So we'll see that shortcut a lot more in this section. Then on the bottom, the square root of 16 is 4. Last one here. This one is really similar to the one we just did, so I would go ahead and try this one. The cube root of x over 64. So first thing we want to do is split this up. So we have the cube root of x over the cube root of 64. Now, one thing to notice here is that let's say that we used the shortcut on the top. We have x to the 1st and the cube root. So what we would normally do is take the exponent and divide it by the index. If we do that here, we would have 1 divided by 3. But because 3 doesn't go into 1, we can't actually reduce this down on the top. So one thing you'll notice the more that you do these, the exponent on the inside, in order for us to simplify this down, or for us to be able to simplify it down, the exponent has to be at least as big as the index. So if this were an x cubed, we could simplify it. Or if it were an x to the 4th or 5th, something bigger or equal to 3. So we're going to leave this as the cube root of x on top. And on the bottom, what times itself 3 times gives us 64? That'll be 4. So a couple things to note here. We are told to simplify because all of these terms that we started off with here had fractions under the radical. And so that is one thing that we don't like to have under radicals. And so if you remember, kind of like with exponents, it's just kind of convention to not leave your answer with negative exponents. Same thing here, except we don't like fractions under the radical sign or the radical symbol. And there's one other thing. So we don't want any radicals in the denominator. Now, we didn't see this here at all. Once they were simplified, we had radicals in the numerator, like we had here and here, but we didn't have any radicals in the denominator. So this is actually something we'll see in section 11.5. 11.5. So that's coming out, not 11.5, sorry. This is supposed to be section 10.5. So it's coming soon, just not right now. All right, so one thing to note here is even though not all radicands, remember radicand is the thing that's on the inside of the radical sign, are perfect squares. But we can still simplify them. Okay, so that's the case with most of them. You can't always simplify radicands or radicals down. Depends what the number is, but let's go ahead and look at simplifying radicals. So you can think of this kind of like reducing fractions. We're trying to get the radicand down as low as possible. So number one here, we're given the square root of 32. Now, one thing you're going to want to try to get down for simplifying radicals, and a lot of the time you'll see like cube root, square root, fourth root, they're not going to go super high. A lot of the times they'll be square roots. So you're going to want to get your perfect squares down pretty well. So like 1 squared is 1. Let me change the color here. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared, 16, 25, and so on. So these are your perfect squares, and you should know them up to about 13 squared, preferably higher, but up to like 169. I'd recommend getting those down. It's going to make your life a lot easier here, because what we're going to do is we're going to use our product rule that we just learned and kind of go backwards with it. So 32, if we think about the factors of 32, we have 1 and 32, 2 and 16, 4 and 8, 5, 6, and 7 don't go into 32. So this is what we have. Now we want to find a perfect square that goes into this number as large as possible. So if you notice, we have 4 times 8, so we could use that. But there's one that has a bigger perfect square, and that is 2 and 16. So I'm going to take this 32 and break it into 2 times 16, which now at this point, I can go ahead and split this up. So if you remember our product rule here, I'm going in this direction. So I'm going to take it and split it up into 2 separate square roots. And so if I go ahead and do that, we have the square root of 2 times the square root of 16. Well, we don't know what the square root of 2 is, but the square root of 16 I know is 4. So this is the same thing as the square root of 2 times 4, which kind of like with variables, we always want to put that term out in front that doesn't have the radical sign out in the front. So we're going to have a 4 square root of 2, or 4 root 2. So a lot of the time, I'm going to go from this step right here to this last step here. You just take the square root of 16 out as a 4, and that 2 stays on the inside. If you want to go through these steps every time, perfectly fine. It's good practice. But once you can go from this step to the step at the end, it's going to make your life a little bit faster. All right, let's go ahead and try number 2. So number 2, we're given the square root of 45. So again, try to think of a perfect square that goes into 45. So go through the factors in your head. So we got 1 and 45, 2 doesn't go into it, 3 goes into it 15 times, 5 goes into it 9 times. So 9 is a perfect square, so I'm going to break this into the the square root of 5 times 9. And now what we're going to do is, because 9 is a perfect square, we can take the square root of 9 out. Make sure you're taking out the square root of 9. So the square root of 9 is 3, and we can't take the square root of 5, so that's going to stay on the inside. Okay, let's go ahead and try another one. This one we're given negative square root of 300. Now, this one looks a lot bigger. If you were to go through and write down all of the factors of 300, it would take you quite a while, because we'd have 1, 2, 4, 3, a lot of different numbers go into 300, but there should be one perfect square that goes into this that kind of stands out, hopefully, and that is 100. So 300 divided by 100 is 3, so we have 100 times 3. And now what we can do, we can take out the square root of 100, so that'll be going outside. And make sure you leave this negative in the front. So it's just kind of hanging out in the front. It's going to stay there. Just make sure it goes in the front, because it's just saying this term right here is negative. So square root of 100 is 10, and we can't take the square root of 3. That stays on the inside. All right, number 4, the square root of 35. So square root of 35 here, if we go through the factors of 35, we have 1 and 35. And then if we test, 2 doesn't go into it, 3 doesn't go into it, 4 doesn't go into it, 5 goes into it 7 times. But if we look at all of these numbers here, these are all of our factors of 35. None of these numbers are perfect squares, which means this one, and depending on the answer that they give you, you'll either say cannot be simplified, or already simplified, something along the lines of we can't do anything else to this because it's already as simplified as it's going to get. All right, let's try a few more of these. So number 5, we're given the square root of 72. And so for this one, I do want to show you 2 different ways of doing this one. They're using the same method, they're just using slightly different numbers. So if we go ahead and look at the factors of 72, try to think of a perfect square that goes into 72. One perfect square that goes into it is 8. And so I can write this as 8. Sorry, not 8. What am I doing? 8 is the number that goes into it. 9 is the perfect square. So if we do 8 times 9 here, we can take out the square root of 9. And so if we take out the square root of 9, that's a 3. That'll be in the front. And then we'll still have that 8 left on the inside. But always make sure you double check your solutions to see if you can simplify any further. So if we look at this one, we can split that 8 into 2 times 4, and 4 is a perfect square. So that means we can take out the square root of 4. And now what you have to do when you already have a number out in front is just a bunch of multiplication. That's all we're doing here. So we're going to have 3 times the square root of 4, which is 2. Leave that 2 on the inside. And now let's go ahead and just multiply those together. And 3 times 2 is 6, square root of 2. Now, that way was a little bit longer. There is a way to do this in less steps. And the way to do that is to find a bigger perfect square that goes into 72. So if you think about the perfect squares, we have 1, 4, 9, which is what we just tried, 16, 25, 36. And if you notice, 36 is half of 72. So I can split this into 2 times 36. The square root of 36 is 6, so we'll take that out in front and leave the 2 on the inside. Whoops, 2, not 6. Notice how we get the exact same answer. There's just 2 different ways of doing it. One way's quite a bit faster, but it really depends on what kind of number you're starting with. If it's a little bit bigger, you might find yourself going through a couple of steps, which is fine. I still go through and do multiple steps sometimes. If you don't really list out all of the perfect squares or all of the factors of the number, you might need to do the longer way. If you're really careful, you can go the shorter way. It just depends. But always make sure you're double checking at the end to see if you can go down any further. Kind of like reducing fractions. You always want to make sure they're fully reduced. Okay, the last one here before we check out how to do this with variables is negative cube root of 54. Now, this is still possible with cube roots and fourth roots, but instead of splitting it up into a perfect square and another number, we're going to split it into a perfect cube and another number. So with 54, we have, actually, let's go ahead and look through the perfect cubes. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, and 4 cubed is 64. Now, if we go ahead and look at what we have here, we want to see which of these perfect cubes over here go into 54. Well, 27 goes into it twice. So let's go ahead, we'll leave the negative out in front, and we're going to split this into the cube root of 27 times 2. Now, if we go ahead and take out the cube root of 27, remember, leave that negative in the front. The cube root of 27 is 3, and then we're left with the cube root of 2. So just taking out whatever cube roots you can. All right, now let's go ahead and look at how to do this with variables. And I'm going to show you kind of a long way of doing it, and then we'll talk about the shortcut, kind of like what we've seen a little bit where you divide the exponent by the index. But first, if we have the square root of x squared, remember that the square root and the square cancel out. And so we just are left with x. Same thing if you have the cube root of x cubed. Those guys cancel out and we're left with x. And so on. So fourth root of x to the fourth is x. And so the nth root of x to the n is just x. So we're going to kind of use this to simplify variables under a radical sign. And again, we'll show you the long way and then we'll do some shortcuts. So number 1 here, we're given the square root of x cubed. Now, we know that we can take the square root of x squared pretty easily. That turns into x. So what I'm going to do is I'm going to split this up into x squared times x. Because if we added those exponents, 2 and 1 gives us 3. So we know that we've split it up and it's exactly the same as what we started with. Now, kind of doing what we did in our first question, we're going to use the reverse product rule and split this up. So we have the square root of x squared times the square root of x. And we know the square root of x squared, those guys cancel, and we just get x times the square root of x. Now, there's a shortcut for this. So let me go ahead and show you the shortcut with another example. So let's go ahead and do the square root of x to the 7th. What we're going to do here is we're going to take the exponent and we're going to divide it by the index. So if we do that here, we have 7 divided by 2. Remember that index is a 2. And so we're going to do this in terms of, we're not going to use fractions. We're going to do this in terms of the whole number and the remainder. So 2 goes into 7 3 times with a remainder of 1. So this 3 is going to go on the outside. So we're going to have an x cubed on the outside. And then we're going to have 1x left on the inside. And that is the shortcut. It's a little bit nicer than splitting it up like this. If we had used the shortcut for this one, we would have 3 divided by 2. That would be 1 remainder 1, which is why we took out 1x, and we were left with 1x on the inside. Now, this shortcut takes a little bit of practice to kind of get it down. So let's go ahead and try some other examples. Number 3 here, we're given the square root of 16p to the 9th. So here, one thing we can do is notice that the square root of 16 is 4. So I can go ahead and just take that out. Now, if we're looking at the square root of p to the 9th, what can we take out? So think about your division. So remember, there's an imaginary 2 out here. So we're going to have 9 divided by 2. Well, 2 goes into 9 4 times with a remainder of 1. That means that we can take out a p to the 4th, and we're going to be left with 1p on the inside. So I'll add that in here. So on these arrows, I'm going to put what we're taking out. So we're going to have a 4 on the outside from the 16. We're going to have a p to the 4th, and then we're going to be left with 1p on the inside. All right, let's try another one. Square root of 25p to the 7th. So doing this one, again, 25 is already a perfect square, so I don't have to split that up. So I can take out the square root of 25, which is 5. And then with the p's, if we have 7 divided by 2, well, 2 goes into 7 3 times, so we can take out 3 p's, and the remainder would be 1. So we're going to be left with 1 p on the inside. And we took out the 5, and we also took out a p cubed. Okay, let's try some more. These ones have both had perfect squares in them. Let's go ahead and try one that doesn't have a perfect square and see how that works. So 72xy cubed. All right, so let's look at the number first. So 72 is not a perfect square, so we're going to have to break that up. So 72, perfect square that goes into 72. We actually saw this one earlier. You can start off with a smaller number like 9 times 8, or if you see the larger number of 36 times 2, that also goes in there. And then I'll leave the xy cubed. Now, what I normally like to do is I'm going to set up, I'm going to leave some space in the front, and then put my square root over there so I can put things away in there as I go. So if we look first, we have the square root of 36. I can take that out in front, and that's going to give us a 6. And then we know the 2 is going to stay on the inside because we can't take the square root of 2. Now, if we look at this x, since we're taking the square root, there's an imaginary 2 out there. Because x has an exponent of 1, which is less than 2, we cannot take any x's out. Because 1 divided by 2 is just a remainder of 1. So that'll give us a 1 on the inside, a 1x. And finally, if we look at the y cubed, we can take some of these out because we have a y cubed, which is bigger than 2. So remember, we're going to do 3 divided by 2. That gives us 1. So we're going to take 1 y out. Whoops. And then we have a remainder of 1. So we're going to be left with 1 y on the inside. So I'm going to go ahead and just make this look a little bit nicer. 6, I'll do it this way. So we have 2xy on the inside. Okay, let's go ahead and try some more. With these ones, it's really all just about getting practice because it's the same process. over and over again, that it can be a little tricky if you don't do a bunch of them. So this one we're given the cube root of -27, x to the 5th, y to the 7th, z to the 6th. A few different variables here. So let's go ahead and look at the number first to see if we need to split it up. We're looking at the cube root now. So 27 is a perfect cube. So I actually don't need to split this up. We can go straight into taking things out. Cube root of -27 is going to give us a -3, because -3 times itself 3 times is -3. So I'm going to put that out in front. Now looking at the x's, we have an x to the 5th. So now that we have an x to the 5th, and we're taking the cube root, we're going to do 5 divided by 3. That's going to be 1. So we're going to have an x that comes out in front. I'll leave a little bit of a space, and then we can fill up the inside. How many x's are we going to be left with? What is our remainder? The remainder is 2, because 3 to 5 is 2. So we'll have an x squared. Now let's look at the y's. So we have a y to the 7th. So we can take out, well, 3 goes into 7 2 times, so we can take out a y squared. And then how many y's are left on the inside? Well, 3 times 2 is 6, so there's a remainder of 1. And then finally our z's. We can take out, well, 3 goes into 6 2 times, so we'll take out a z squared. And then what is the remainder? Well, z to the 6 divided by 3 is exactly 2. There is no remainder, so we don't have any z's left on the inside. So I'm going to fix this so it's not quite as long. We're left with the cube root of x squared y on the inside, and then we have -3 x y squared z squared on the outside. All right, let's do 2 more. So this one we're given negative cube root of, let's do 16 x to the 4th, y to the 5th. So I would go ahead and try this one now that we've done a couple of them. So if we go ahead and try simplifying this one, let's look at the number first, and we're doing the cube root. Since that's the 16, that is not a perfect cube, but there is a perfect cube that goes into 16, and that is 8. So I'm going to split this into the cube root of 8 times 2, and then x to the 4th, y to the 5th. And now leave this negative out in front. The cube root of 8 is going to be 2, because 2 times itself 3 times is 8. And now x to the 4th, so 4 divided by 3 is 1, so we can take out 1x. And how many x's are left on the inside? Well, we're going to have 1x left on the inside. There's also this 2 on the inside, so I'm going to put the 2 first and then our 1 remaining x. And let me draw that one in because I didn't do that. So we're taking out an x. Then if we look at our y's, we have y to the 5th. 5 divided by 3 is 1, so we can take out 1y. And we'll be left with, well, 5 divided by 3 is 1 with a remainder of 2. So we're left with a y squared on the inside. So again, this is as far as we can go. I'll just kind of squish those up next to each other so they look a little bit nicer. And this is our final answer. Okay. So let's go ahead and do one more of these, and then we have something called the distance formula, which is just the last little kind of random bit of information at the end of this section. So number 8, we're given the cube root of x to the 10th over 27. Now this one's going to use our quotient rule, and what we just learned about simplifying radical expressions. So if we look on top, we're going to split this up. So we have the cube root of x to the 10th on the top over the cube root of 27. Now the cube root of x to the 10th, we're going to use our division shortcut here. So 10 divided by 3 is 3, so we'll take out an x cubed. And then on the inside of our cube root, we're going to have a remainder of 1. One really kind of common thing to forget when you're doing this is kind of losing this cube root. Make sure your cube root doesn't turn into a square root once you take things out. It's still the same kind of root. We're just taking things out of the radical. So be really careful. If you're putting answers into MyMathLab and it keeps telling you that your answer is almost right, I'm not sure how helpful their hints are with these, but a lot of the times that's something I'll see. So just don't forget to keep your root. All right, and now on the bottom, the cube root of 27, well, 3 times 3 times 3 is 27, so that's just a 3. Okay, so the last part of this section, like I said, is kind of, it's related in the sense that we need to know how to simplify radicals before doing this, but this is the distance formula. And so this might have been something you saw in geometry, a little bit in algebra, but the distance formula gives you the distance between 2 points. So let's say we're given x1, y1, and x2, y2. So kind of like what you have when you find the slope. So the distance formula is d, so distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. We can't cancel out the square root in the squares because of this addition in between. So you do have to go through and do these steps. Simplify on the inside and then take the square root. So the reason why we're doing this, if we were to go through and look at the distance between, let's say, these 2 points here, what this actually comes from is the Pythagorean theorem, which we've seen a little bit. Pythagorean theorem tells us that if we have these two sides, A and B, with a hypotenuse of C, then A squared plus B squared equals C squared. And so what they've done is to find this distance C, they've square rooted that right side to get rid of the square. But then if you do that to the right side, you also do it to the left. So we have the square root of A squared plus B squared equals C, which should look kind of similar to what we have over here. The only difference between this is A is that vertical distance, that's our change in Y, and B is the horizontal distance or the change in X. So technically it doesn't matter if the X's or the Y's go first. Just make sure that the X's go together and the Y's go together. But remember, addition you can do in any order. Okay, so let's go ahead and just do 2 examples. So we're told to find the distance. And so in each case, we're given 2 different points. So number 1 here, we're given 2, -1, and 5, 3. So using this distance formula here, if you want, you can label these x1, y1 and x2, y2. And this is kind of like when you find the slope, you want to make sure that you're going in the same order and you're keeping the x's together and the y's together. So we're going to have the square root of, in parentheses, we're going to do x2, so 5, minus x1, which is 2. Square that, and then plus y2, which is 3, minus y1, which is -1. So I'll put that in parentheses, inside the parentheses. And then square that. Now, if we go ahead and start simplifying, you want to simplify from the inside out. So we're going to simplify inside these little parentheses first. And in general, I'll keep this in parentheses, but I'm going to simplify it. So we have a 3 squared plus 3 plus -1. 3 minus a -1. Add the opposite. So 3 plus 1 is 4. So we have 4 squared. And now, before you add, we need to do our exponents. So we have the square root of 3 squared is 9, plus 4 squared is 16. And now, still working on the inside, 9 plus 16 is 25. So we have the square root of 25. And if you can, you want to make sure that you simplify. So square root of 25 is 5. So the distance between those 2 points is 5. We'll just say units because we weren't given any units here. Okay, so for these ones, it's a matter of plugging in and then just making sure you're simplifying in the correct order. So let's go ahead and try one more. So the distance between -3, 2 and 0, -4. All right, so again, we're going to have the distance of, we're going to subtract our x's. So we're going to have x2 minus x1. So we're going to have 0 minus -3. Again, be careful with that negative. Squared plus -4 minus 2. So -4 minus 2, and then square that. So simplifying here, again, simplify inside those parentheses first. Let me actually do that in a different color. So inside these parentheses. So 0 minus -3 is the same thing as 0 plus 3 if we add the opposite. So we have 3 squared plus -4 minus 2 is -6 squared. So this is why I keep the parentheses, because -6 squared versus the opposite of 6 squared are 2 different numbers. So make sure you always keep those parentheses. Simplifying a little bit further, the square root of 3 squared is 9 plus -6 times -6 is 36. Adding those two together, we get the square root of 45. Now, this is not a perfect square, but we can simplify it. So we want to go ahead and check to see if a perfect square goes into 45, which it does. And what perfect square would that be? Well, 45 is 9 times 5. The square root of 9 is 3, so we're going to take out a 3. And we're left with a 5 on the inside. So it's 3 root 5 units between those 2 points. And this is like a straight shot between the points, assuming you're not, going off anywhere between the points. All right, so that's 10.3, our next section. For next week will be section 10.4. That'll be adding and subtracting radical expressions. So we're still working with radicals. Then we'll get into multiplying and dividing them. And then we'll eventually see some equations and our complex numbers.